Okay. So, this is the tutorial class based on the lectures 11 to 15. Here we will discuss few problems. Tutorial 3. Okay. The first problem is there any infinite set in R which has no limit point in R. In fact, it is very simple problem. What the Bolzano-Restas theorem says? The Bolzano-Restas theorem says that every infinite bounded set in R, every bounded infinite set in R has a limit point. So, in fact, if we want an example of an infinite set which does not have any limit point, so it must be taken to be unbounded. Therefore, the required example will be set of natural number 1, 2, 3. It is infinite set, but unbounded. So, it does not have any limit point in R. So this is exercise based on the Bolzano-Restas theorem. Okay. And next example also based on the some Hannibal theorem. Give an example of an infinite set which is compact in R, So, what is the what is the Hannibal theorem says? The Hannibal theorem says that a set in R is compact. A set in R is compact if and only if it is closed and bounded. So, we wanted an example of an infinite set which is compact in R. So, an infinite set, if it is closed and bounded, then it is compact. Is it not an infinite set which is closed and bounded, compact. So, for example, choose the set A B, set of all points lying between the closed interval A B. So, this is R, set of X such that this happens. Now, this set A, this is the set A. This set A is infinite. The number of real numbers between A B is infinite and also closed because A B, all the limit points of the set A B are the A B itself, because the limit point of this, because the closure of A bar coincide with A, and further it is bounded. A set is said to be bounded if there exists a constant m such that mod of x is less than or equal to m for every x belongs to the set A. Then x A is said to be bounded if there exists m greater than 0 such that this condition is satisfied. So, here it is bounded because the interval, all the line points does not exceed by b, all these. Therefore, a set is bounded and all the limit points lie closed and bounded. So, this is an example of an infinite set which is compact. Therefore, A B is compact. An infinite set which is okay. Next example, if K be a closed subset closed subset of R such that every infinite subset of K, every infinite subset of K has a limit point in K, then K is compact. Solution. So, we will use the Henny-Wheeler theorem. K be a closed subset of S such that every infinite subset of K has a limit point in K, then K is compact. So, what we wanted to show K is bounded. In order to show K is compact by Henny-Wheeler theorem, because closed and bounded set are compact sets. Okay. Now, what we given K is a closed subset of such that every infinite subset of K has a limit point in them. So, B wanted to show this K is bounded. Let us resume by contradiction. Suppose K is not bounded, unbounded. So, once it is bounded, so there exists a sequence x n in K such that say x n is greater than x n minus 1 plus 1. It keep on increasing. So, it is an unbounded set. Okay. Since it is unbounded, therefore, the set of these points x 1, x 2, x 3 and so on satisfying this condition, satisfying the condition x n is greater than x n minus 1 1 is unbounded set, has no limit point, because say if I take x naught, then x 1 becomes x naught plus 1, x 2 becomes x 1 plus 1, that is x naught plus 2, and x n becomes x naught plus n. So, as n tends to infinity, it will go to infinity. Therefore, it has no limit point by construction. Now, this contradicts our assumption that K in K, the every infinite subset has a limit point. This contradicts therefore, this contradiction is reached because of our wrong assumption. Therefore, K should be bounded. So, K is already giving closed, K is bounded, hence K is closed and bounded implies K is compact by Henny-Wheeler. Therefore, this completes the results for. Next is very simple, what is a fundamental question, so that the Cantor set is a compact set. Is a compact set. What is Cantor set? If we take the interval 0 1 and divide into 3 parts, 1/3 and 2/3, and remove this one, remove this portion, leaving 1/3 and 2/3. Again you further divide into again and remove this part and leaving these points. So, the remaining set is a Cantor set. Okay. Now, this Cantor set obviously is a closed and bounded. And bounded because all the points lying between 0 and 1. So, it is a bounded set, and since it is closed, why it is closed is because the 1/3 is the limiting point of these sequence of the point which are dropped. So, 1/3 is the limit point of all these point here as well as here also. Okay. So, these are the limit point of the set one, and this limit point belongs to the set Cantor set. Therefore, this Cantor set is a closed and bounded, hence it is compact. And as a corollary of this, we can say that so that every point next every point, so that every point of the Cantor set C is a limit point of the closed interval 0 1 minus C, and then solution is very obvious. So, if we remove as explained above, we are removing the middle third, and the end points of the removed portion remains fixed in the, therefore, this end limit point. Okay. Since limit point of the removed portion is these points. C is the limit point of this portion. Okay. C is the limit point of the limit portion is in the Cantor set. Okay. So, not this be removed. So, this is the limit point of these sequences, this is the limit point of these sequences. Therefore, limit point of the removed intervals, if you take any sequence in the removed interval sequence whose limit point will be the point of this thing. Therefore, this is justified. Okay. So, nothing much to prove it. Okay. Now, suppose we have what is the derived sets? Find the derived set of A, which is 1 minus 1, 1 and a half, minus 1, 1 and a half, 1, 1/3, minus 1, 1/3, and so on. Okay, derived set. Solution. Derived set means set of all the limits point of the set A is called the derived set. Set of all limit points of the set A is the derived set. So, here the if I take minus 1 and 1, we claim that minus 1 and 1 are the only limit points of the set A, because any neighborhood of 1 or minus 1, any neighborhood of 1 and minus 1 contains infinite number of points of A. Therefore, 1 and minus 1 is the only limit point and nowhere else. So, derived set A dash will be 1 and minus 1, that will be the derived set for this. Okay. Okay. Next example is, let D A B R is the set of all point x y such that x minus a whole square y minus v whole square is strictly less than R. Then illustrate the closeness and openness of the following. Then illustrate illustrate the closeness and openness of the following sets. The sets are 1 x, which is d 1 x, d 0 0 1 union 1 0 union d 2 0 1. V is W d 0 0 1 union d 2 0 1. Okay. So, solution is, what is our DAB? DAB R means set of those point x y such that x minus a whole square y minus b whole square is less than equal to R. So, basically it is the less than R, not equal, less than R. Okay. So, if we take the d 0 0 1, then d 0 0 1 is the set of all x y such that x square plus y square is strictly less than 1, while the d 2 0 1 is the set of all x y such that x minus 2 whole square plus y square is strictly less than 1. So, if we plot this thing, then this is our zero 0 1 and this one is, so this is 0 0, this is 2 0 and this is the set of these elements and this element, excluding this part is excluded, these portion are not there. Okay. This portion is not there, but in the set A, in this example A, we have added the point 1 0. So, this point is also added, this point is also added. So, this is our 1 0. So, when we take the A part, the x is the union of these points including this, but what is this is? The derived set x dash is the complete x, derived set is d 0 0 1 and union of d 2 0 1, where this close sign shows where d 0 0 1 we mean the set of all x y such that x square plus y square is less than equal to 1. Similarly, d 2 0 means. So, we have taken the point over the boundary. So, set of all point inside together with the boundary is the closed set. So, the limiting point of the set x is the point which are lying inside this disk as well as on the boundary. But what happens to this x dash? So, x dash, is it a subset of x? No, because x does not include the point on the boundary. So, it is not the subset of x. Therefore, all the limit point of this set together is not contained inside it and totally. Therefore, this x dash and the derived set x bar is not subset of this, therefore, is not closed. It means x does not include all of its limit point. So, x is not closed, while on the point 1 0 1 is not an interior point. So, it is not closed. But what about the d 0 0 1? D 0 0 1 and d 2 0 1 are open sets, So, their union is open. So, d 0 0 1 union d 2 0 1 is open. but what is our x? X includes point 10 also, which is 10 also. So, which is not an interior point, of x, because if we draw any neighborhood, if we draw a neighborhood about the point 10, then the number is lying outside of it. This is 100, this is 1, this is another, and if I draw the neighborhood will be this one. This is the neighborhood of 10. Now, here these points are not there, does not belongs to x. So, 10 is not a interior point, therefore, x is not open also. So, it is neither closed nor open. So, it is while in case of second, what is the W? W is D001 union D201, that is 1. So, obviously, it is an open set, because it is a union of the two open sets. So, it is open, therefore, W is the open sets. Next example is, which of the following sets are dense? In R2 with respect to the usual topology. The first set is set X ordered pair X y belongs to R2 such that X belongs to N. B is W X y belongs to R2 such that X plus y is a rational number. X y is rational number, and C is S x y belongs to R2 such that x square plus y square is 5, while the D is T x y belongs to R2 such that x y is not equal to 0. Okay. So, let us see the solution. Before going to the solution, let us define the dense set. What is the dense set? Let X t be a metric space a subset A of X is said to be dense in X if the closure of A coincides with X. The meaning of this is, that is, every point of X is an adherent point of this set, that is, every neighborhood of the point intersects with X. So, the meaning of this is if we take this is x and this is our A, then x, a subset A of x is said to be dense if the closure of this is coinciding x, or in other words, if we picked up any arbitrary point of x and draw the neighborhood around that point, then it must include some point of A x. So, every inherent point of A, every neighborhood of the point intersect with A. So, whatever the point A, it will intersect with A, then such a set is point is said to be adherent point, and if the closure of A coincide with x, then A is dense. Now, the problem is like, what is the first problem is x by belongs to R is 2, where x is a natural number. So, let us see, suppose these are the natural number 1, 2, 3, these things are there. Okay. Now, x is a natural number, say 1, 2, 3 and so on. Now, all the points in between n and n plus 1, if we take this is suppose n and this is say n plus 1. So, these points and this point in between this are neither the limit points. So, the points in between n plus 1, where n is an natural number, in between n to n plus 1, that is in between x equal to n to x equal to n plus 1, where n is a natural number. So, in between these steps are neither the limit points of the set x nor the points of x itself, nor the points of x. Therefore, when you take the closure of this set of all limit point of this, it does not cover the entire R. Therefore, it is not equal to R 2. Therefore, x is not dense in R 2. The second example shows that when we take the x y such that x plus y is rational number. So, if we take any point a b, so take any point a b, then in any neighborhood of the point a b, we can find infinite number of points x y such that either x or y is irrational, because rational and irrational number they are very close to each other. Okay. So, this implies that x plus y is a irrational number always, and once we are having the irrational point, then so we get every neighborhood. Therefore, every point of R 2 is a limit point of W, because W consists of those points W which are rational points. So, every point of R 2 is a limit point of W. Therefore, W bar is R 2, hence W is dense. Is it not? Because if you take any point x y in neighborhood, it contains both the point irrational and irrational. So, when you take the x plus y, it becomes a irrational. So, this point x plus y becomes the limit point of these irrational points. Therefore, its W bar becomes R 2. Okay. The third case C, in that case the closure of S bar, which is basically the thing is x plus y x square plus y square is 5. So, closure of S, which is S, is not equal to R 2. Therefore, S is not dense, because it does not have any point of this is not the is the limit point of itself, but not the sequence, any neighborhood does not belongs to that. Okay. So, it is not there. D, when you take the D, the t bar equal to R 2. What is the x y? If we take this, then x y is not equal to 0. So, basically we are getting this except this line where it is 0. So, it is closure of this R 2, therefore, T is dense. That is all. Thank you very much.